Hi everyone, so in this video we will be working on this first example in this chapter 2, worked example 2.1, and of course you can always access these problems using the link on the actual PowerPoint or PDF. Obviously on this video you can't directly click on it, but I will have it in the description of this video. So in this problem, we will be predicting the direction of a dipole moment. So we don't necessarily have to think about or calculate the actual values, but we do need to understand and reference that trend of electronegativity that we learned, which was, and if honestly, if you had that periodic table that had the electronegativity values on it, that would be a lot better. But we know that electronegativity increases this way on the periodic table. So it's highest to the top right. I had to think about that for a second. And knowing that trend is really going to help us here. So we have this compound, methylamine. It is CH3NH2. We are going to need to draw it, right? The 3D drawing. So we're going to need the molecular geometry and the shape of it overall, basically, in order to show which direction the dipole moment is going. So our strategy is to look for any lone pair electrons, to identify any atom with an electronegativity that is different from carbon, meaning higher. And of course, we have our handy rule of thumb that oxygen, nitrogen, fluorine, chlorine, and bromine, which all happen to be located right there, that these are very high electronegativity in comparison to carbon. So we know that electron density will be displaced in the general direction, meaning that the electronegative atoms will have the electrons around it. They're hogging it. Remember, that's how I like to say it. So before I move on, let me decrease this size. And of course it doesn't want to. Okay. So let's go ahead and try to draw this, right? Remember, we're practicing, so don't stress out if something doesn't come out exactly the same as this example. If you pause it and try it on your own, don't stress out. We're practicing, remember. So we have to go ahead and draw the Lewis structure. That, again, is a very important part of this class. So we need to draw CH3 and H2. Remember, step 1 is always to calculate the total valence electrons. So we have 1 carbon. Let's add up the hydrogens. We have a total of 5. And then we have a nitrogen. How many valence electrons from carbon? We know that is 4 valence electrons. VE with the superscript minus, that's how I denote valence electrons. For each hydrogen, we know that has 1 each, so a total of 5. And then nitrogen, 1 nitrogen specifically, that means we have 5 valence electrons. So we need to add this up, just zooming in so you can see a little better. 14, total of 14. Okay, let's go ahead and try to draw this. The center atom is always the least electronegative. So this actually ties really well into this because that's what we're looking at. And that is going to be carbon. And remember, we always start with just single bonds and then we slowly fill in. Now, notice that this compound actually shows you that hydrogen, there's 3 hydrogens connected to this carbon. So that's what we're going to go ahead and follow. And then there is a nitrogen connected to a carbon. And this right here is telling us that there are two hydrogens connected to this hydrogen. Sorry, this nitrogen. They all start to sound the same. Okay, so let's count up the valence electrons. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have a total of 12. We are missing 2. Carbon's happy. All the hydrogens are happy. Carbon has its octet right here. All the hydrogens have their duet. So the only one missing its happiness or, octet is nitrogen. So we actually have to put the remaining 2 valence electrons right there. So that's our structure. Now we need to think about how this would look 3-dimensionally. And hopefully you remember that there are some electron geometries and molecular geometries. So I am going to go ahead and paste our geometries here so that we can review this briefly right before going into assigning the shapes to each section of this compound. So this shape, our tetrahedral, is usually going to be most relevant for most of carbon compounds. So I want you to remember that and look at the fact that if we cut off that extra hydrogen right here, we have this right here, this part, as part of our compound already. So we know that this, remember, you can always use your resources. So this right here around this carbon is tetrahedral. So if I draw it using our dashes and I draw it more similar to our example, doesn't have to be perfect, but I can say, there's a wedge, there is a dash, right? There's one coming out of the plane, one going to the back, and then we have a hydrogen. Now, remember, there's 2 in plane. So this can actually be the nitrogen that's also in plane. Now, nitrogen has 4 regions, electron regions around it. It has that lone pair. It has 3 bonds. That means it's also going to be tetrahedral. So we can have one of them being, we can have one of the hydrogens being in and out, right? Front and back. And then we can have the lone pair as part of the plane. And in terms of right, we're kind of on this tangent, but there's a reason to this, right? How is this affecting the dipole moment, right? That's what we ultimately want to come back to, right? So we know that there is a polar bond between nitrogen and hydrogen. Here. We know that there's a polar bond here. And we know that there is a lot of electron density here. So I would say that the dipole moment as a whole is this way. Now, did we really need to draw this in 3D form? Yeah, just because we wanted to see, how this would be interacting with the carbon. side of things. And you can see here that we drew it different, but overall, we have the same idea, right? So this is what I'm referencing about how it's different, but same idea. The fact that we have the nitrogen going, the head of the arrow, meaning where it's more negative, right? This area is slightly negative, this area is slightly positive. The fact that that matches says a lot. And that's mainly what we wanted to figure out. The dipole moment points generally from the CH3 to the lone pair. That's exactly what we did. So overall here, again, what we were trying to kind of put together was what we reviewed from last time, which was drawing Lewis structures, right? That's very important. Understanding the electronegativity trend, and then finally how to assign overall dipole moments based on what we know so far in this chapter.